I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
All right, so we're going to be looking at vectors today, and complex numbers can be written as vectors, and so hope you enjoyed that introduction. I would think most of you have seen that movie before, but it is true what they say. So here we go. Our objectives, we want to represent complex numbers as vectors in the plane, and we want to be able to add vectors. So a vector is a directed line segment. It has both magnitude and direction. They're both important. It's not just like a ray where just direction is important, and a segment, a regular segment, which is just the length that's important. It's direction is important and its length is important. Imaginary numbers can be represented as vectors. The real part represents the horizontal distance from the initial point to the terminal point, and the imaginary part represents the vertical distance from the initial point to the on the horizontal axis. Sorry, that's written wrong. To the terminal point. So we're going to look at vectors and writing them as vectors. So drawing vectors, drawing complex numbers as vectors, you're going to locate the initial point and the terminal point. Now, I probably should have put this part right here after this. If there's not an initial point given, you just go ahead and use the origin. The initial point can go anywhere, but if nothing's given, the easiest is usually the origin. There might be some cases where it's not. So we're going to locate the initial point and terminal point. We're going to draw a line segment from the initial point to the terminal point, and we put a half arrow to represent that it's a vector. You're going to put that at the terminal point. It shows that it's a vector as opposed to a ray. So let's graph these as vectors. It's pretty simple. So this isn't given. This first one is not given an initial point, so we're going to start at the origin at our 0 point, and we're going to go to the right 3 because the real part's 3, the imaginary part is -4. We're going to put our 2 points there, and we're going to go ahead and draw in that vector, and we put a half arrow. So we just put part of an arrow there. That was a rough drawing, but that is our vector for 3 minus 4i. And same idea for the rest of these. Again, this one, we'll go down to this -3i here. So we'll start 0 again. This is I, so that has to do with our vertical. So we're going to go down 3. And we're going to put a half arrow on there. So that's a vector that represents -3i. I mentioned before that you don't need to start at the origin. This, if we did this over here, let's just pick, this is our initial point. We could just still go down 3, 1, 2, and 3. That vector also represents -3i. So it doesn't matter where you start. Come up here to -2 plus 3i. -2 tells us, so we'll start at the origin, that's our initial point. -2 is our real part, so that has to do with horizontal, so we'll go back 2 and then up 3. And we'll draw that segment. And there's, sorry, that vector. Again, that could be anywhere on our graph. We could have started here and gone up to here. Same thing. And then 2. 2 is a real part, so that tells us horizontal direction. So we'll start at the origin. We'll go right 2 because it's positive, and we'll put our half arrow there. So those are representing complex numbers as vectors. That's all you do. Here this is a little different. It does tell us an initial point, so use -2, -3 as the initial point and draw the vector 4 plus 3i. So -2, -3, that's our initial point, and then 4, so here's our initial point, 4 plus 3i, so Our real part is 4. That's horizontal. And then vertical is 3. So we'll go 4 plus 3i. That's just starting at a different point. We can start at 1, 3. There's 1, 3. And we want our horizontal part to be negative 3 and our vertical part to be negative 2. So that would be left 3 and down 2. There's our end. And there's our vector. So we can, again, we can start anywhere on there. Here there's vectors. This next example, there's vectors given already. And we want to state what the vector is, the complex number that's being represented by that. This, we see here, this first one is, it's horizontal, which is the real part, is back 3. And then going up 1. So our real part is negative 3 plus 1i, or just plus I. Over here, our real part is, we're going right 2. And our vertical part, which is our imaginary part, is up 4. So this is 2 plus 4i. And that's all we're doing. We start from the initial point, figure out the horizontal. So start from the initial. The horizontal, this is 4. So that's our real part is 4. And we go up 1, so our imaginary part is 1. And again, here's our initial point. Our horizontal is 4. So that's our real part. And now we're going down 2 on for our vertical, so that's minus 2i. And those are the complex numbers represented by those vectors. So we should be able to draw the vector given the complex number, or if we have the vector already, we should be able to figure out the complex number. So vectors have two important parts, their length and their direction. So length, we learned about this before, it's just the absolute value. We've found the absolute value of complex numbers. So we learned that, so absolute value of any complex number a plus bi is just the square root of a squared plus b squared. Can you remember where that came from? Why it was the square root of a squared plus b squared? It was from, we used the Pythagorean theorem. We drew a right triangle and used Pythagorean theorem. And then direction. We would need a protractor or trig to determine the direction. So we haven't done trig yet in this course. We will do that later, and then we could come back to this and we could find the direction in which these things are going. So find the length of each vector. So we're not doing direction, we're just doing length right now, which is really just a review for us because the length is the absolute value of the complex number. So really, to find the length, we're going to take the absolute value of negative 2 plus 4i, which we learned is really just the square root of a squared plus b squared. This is the square root of 4 plus, got ahead of myself, plus 16, which is the square root of 20. Simplifying that, as we learned earlier, that is going to be, I'll write out a little bit of the work here. 20 is 2 squared times 5. So this is 2 times the square root of 5 is the length of that vector. Next one, just the same idea, more of the same. So really we're going to find the absolute value of this, which is the square root of a squared plus b squared. That's 9 plus 5 squared is 25, which is the square root of 34. 34, if you're going to try to simplify square root of 34, 34 is 2 times 17. There's no perfect square factors in there. And then this one, again, absolute value of this will help us find the length, which is simply the square root of 2 squared. So it's negative 2 squared, although it doesn't matter because a negative times a negative is positive, plus b squared. And so you get the square root of 4 plus 9, which is the square root of 13. So the length of this vector, negative 2 minus 3i, the length of that is the square root of 13. And so length is the absolute value of the complex number. Direction, if we drew in the vector, so let's just hop back up to this. If we wanted to find the direction of this example here, the direction of this vector, we could put a protractor on here and measure the angle, and that could help us find the direction of that vector. We want to add vectors. So really adding vectors for right now, because we're not really dealing with the direction as much. They have direction, but we aren't working with those because we don't have our trig yet. Adding vectors is really going to be easiest just by adding the complex numbers, and we learned how to do this several lessons ago. We just add the real part, 3 plus 7 is 10, and then add the imaginary part. 4 minus 5i is negative I, and that's our new vector. We can add vectors graphically. And to add them graphically, we're going to place them head to tail. So we're going to write our first vector in, and then start our second vector from the head of that one, the terminal point of that one, to draw our next one. So the sum here, as you see, the sum, known as the resultant, so the sum of two vectors, is the vector that connects the first initial point with the last terminal point. So we'll look at a couple of these, a few of these to see. So we'll start with this first one. Seems obvious we should start with the first one. We got 1 minus 6i. So 1 minus 6i, we'll start at the origin. 1, so we're going to go right 1 and down 6. That's here. And so we want this vector. It's a rough drawing of a vector. We're going to add 3 minus 2i. So 3 minus 2i. So what we're going to do is we're going to start here at the part we just ended at, and we're going to go right 3. So we're going to go right 3 and then down 2, which will bring us to here. All right, so we took our first vector, 1 minus 6i, and then 3 minus 2i, and our resultant, remember the resultant's the answer of these, goes from the original point, the original initial point, to the ending point. And we can see, hopefully, that point that we're at now is 4 minus 8i. And I know it went a little off the graph, so it's a little harder to see, but that's 4 minus 8i. So that's how you can add these things, these vectors. Let's look at the next one here. I'm going to try something different in doing these. These arrows won't look exactly how we want them because they have the 2 arrows instead of the half arrow, but well, we got a 3 plus 2i, so which means we're going to go right 3 and then up 2. That did it in white, so let's do this in blue. Right 3, up 2. There's our first vector. From there, we want to go negative 1 plus 4i. So that's back 1, and then up 1, 2, 3, 4. And our resultant vector is from the initial part of the first one to the terminal part of the second one. And then we can see there that the answer to that is 2 plus 6i. So we're looking at this red vector over 2 and up 6, so 2 plus 6i. We also here can add 3 vectors. As you notice, this next one has 3 vectors. No problem, we can still do that. We have 6 plus 2i, so we go right 6. 1, 2, 3, 4, 5, and 6. I know that's off a little bit. And then plus 2i, that's going to bring us up to here. From there, it's minus 5i. Minus 5i, that's the imaginary part, so we're just going to go down 5 from there. 1, 2, 3, 4, and 5. And then from there, we're going to go use our minus 3 plus I. So the minus 3 is backwards 3. 1, 2, and 3. And then plus I is up 1. And so it's bringing us back around. And our resultant is from the first initial point to the last terminal point. And so this one ends up being 3 minus 2i. And so that's how you can add vectors graphically. Our objectives, again, represent complex numbers as vectors, and then add vectors. We can add vectors algebraically, which really is the easier way. Here we added algebraically. We added the real part and the imaginary parts. We also can add them graphically, which you do need to know how to do. And that finishes our chapter on complex numbers.